Okay, so I'm just gonna go through with the fundamental of hyperspectral imaging um, for SpecIm IQ. So, of course, I will just go through the slides, and later on, I will show how to use the SpecIm Insight software. So, yeah, so actually, the training is divided. I mean, the theoretical is divided into three different parts. First will be concept of spectroscopy. So we talk about how spectroscopy works, how I mean the basic method of operations of spectroscopy, uh, how it is, what it is, and what does it do. And then we talk about hyperspectral imaging. So in hyperspectral imaging, we'll talk about imaging system and how does it relate to hyperspectral imaging and how does it work as well. Um, and then we'll talk about data analysis, data acquisition analysis. This is more on an treatment of the data after we capture the image of a hyperspectral image. Okay, so yeah, so I'll go through all of it. Uh, so yeah, okay. So as we know, spectroscopy is a concept of how matter react under electromagnetic radiation, or basically like where we have a sample and a spectrometer. Well, usually it was more of a sensor, yeah, or spectrometer sensor, and you have like an emitter for common type of spectroscopy, like in kartoshka, like in industry, it would be having sorry having a laser shooting to it, and you will scan like an IR range. How to say spectral to actually identify the molecule, for example. So this is how it's usually being done. And in fact, when we talk about spectroscopy, we also first want to talk about light source. As you know, light source is actually just a photon traveling in a form of particle, which is as a photon or a wave. Typically, for our eyes, we have this visible light, so around 790 to 700 390 to 700 nanometers. So it's basically the visible light that we human can see. But in fact, for spectroscopy, you usually playing in a range of infrared, but some actually play in UV light as well, ultraviolets. But regardless, for us human, we actually looking at visible light. And in fact, for spectroscopy, they usually look in infrared. There's a reason for this. It's usually because they are better at making a molecule react. So this is actually quite important because this is actually how most of, for example, lights or molecule give out their signatures. In fact, light itself give out a lot of signature depending on what, how to say, what's the source of the light. For example, I have another slide here showing that emission of light or color of flame actually here emitted using different element. In fact, this is why it's kind of important on how to distinguish chemical compound or elements based on light, because they all actually give different signatures. They give different color of light. And here's just a basic example of lithium, um, sodium, potassium, rubium, cesium, calcium here, strontium, barium, and C copper. So look, as copper give green color, lithium give red color. I mean, if you already know the basic, you should have already known that. Oh yeah, this is this element corresponding to this color. So, in fact, it's very simple how this light being portrayed or projected is actually through what we call excitation mode of an atom, for example, here. In fact, this is not just happen in atom, it also happens in a molecule as well. So what happened is that here in the center here, I have a image of a Bohr's model of atom, and you have here a center, which is a nucleus, which is your proton and neutron. But you have around here is what we call valence. It's a what we call subshell of electrons, where electron is located. So what happens is that when there is a light shooting through and hit the electron become very unstable, because what happens is that it absorbs this light and the energy increases. So what happens is that it jumps to another subshell, and in this jump of subshell, it's actually he doesn't really like it. He likes to jump back to the what we call ground state, the most stable state, because it's weird to have like some sort of empty shell. Uh, so this is what we call a Pauli exclusion principle, where they want to jump, and if it's unstable, they want to jump back, which is basically to fill up the empty holes. So when the electron wanted to jump back to its ground level, the photon is emitted, and this photon is actually what gave out the color of here is the flame. Because well, why? It's because so why? Okay, why does it have different color of flame? So if you remember, if you know a periodic table, they have like a few, how to say, number what do you call, the identity of the atom depends on how much electron and how much proton and neutron it has. So usually all of these element actually have different number of electron, therefore different number of subshell or holes or empty slots within the valence shell. So that's why it have different colors, meaning it's just jump between different holes to a different. So each atom actually have different number of or different position of holes, therefore giving out different colors. So this is just how spectral distribution works. I mean, how uh, light happen to be. Why does it have different color? So just remember, basic simple is basically an electron jumping to a different level, and say like, oh yeah, it's not too comfortable to sit here because there's a hole below, so I want to go back to the hole. And when it goes back, the photon shoot out. The photon that was shoot out is a different colored photons. So that's sorry, no, the photon that shoot out was the emission of light from the molecule. So yeah, and in fact, this is what gave out the halogen spectral distribution. In fact, all this jumping out actually gave out. They all actually give out spectral distribution. In halogen lamp, you can see the distribution is quite huge, because they also excite. I mean, when the photon was shoot out, it's also shooting out the photon on this IR range wavelength. So you can see the distribution is higher here, and there's also some visible range. I'm sorry for that. One moment. Yeah, and for electron, sorry, no, for LEDs, there's a different type of LEDs. There's a gallium nitrate and indium gallium nitrate LEDs. So it depends on your color of LEDs. And usually, if you are using blue LEDs, there is a indium inside it. And it depends on also how, but they usually give out the same sort of distributions. Yeah. So this is all actually due to the molecule, which covering, for example, the what do you call, the LEDs? Not just the covering, actually, even what it made of, because the way uh, how to say this, the way how uh, LED were made is actually by by two different maybe I can draw a bit. So in LEDs there is this oh, I cannot draw it. Yeah. Okay. In LEDs there is this thing what we call platings. Oh, yep. Two plate, positive, negative. They're usually made out of indium or gallium. What happens is that during this time there is a transfer of electron jumping from one side to another side. Oh, I don't know why there's a line. So during this jump, the photon was emitted like this. So this photon actually give out the color of these LEDs, and this happens all the time. I mean, constantly in LEDs. In fact, how does this how to say photons was emitted on how they know that this is the color that they're looking for is actually what this two plate is made out of. So this is how they are made, how they know what, how to say, what photon does it come out as. Yep. Okay. And in fact, our sunlight also give out like a very good spectrum. This is because sunlight not only burn helium, it also burn hydrogen. It's also burning what else? Iron, also burning sulfur. It's burning a lot of molecule or atom at the same time, which giving out this huge range of spectrum. That's why you can see it goes even further than infrared. So yeah, this is why sun have one of the best spectrum distribution for hyperspectral study. Okay, moving on. So of course, in industry, we have already built out standard illuminants. I understand that if you're already in the industry, you should have known some of this standards of illuminants, and you know like the 65s and everything. And this also gave out some certain type of distribution of spectrum. So it depends on what standard you're following. You might want to follow it all the time. You can't just use one today and then change another tomorrow. Yeah, okay. So all these actually are important factors in spectroscopy, because spectroscopy actually is this concept of shooting light into molecule, which then later on you would read the spectral distribution. Well, we will see some example later on. Mm. Now we're going to move to reactivity. So actually, what was the reactivity? So it's actually we're going to talk about how compound or molecule or atoms reacting, and what give out what is the output of this um, how to say reaction. So first of all, I will show you this example here. We have a PU. Not too sure what this is actually, but you can see there's an oxidation number here. So this oxidation number meaning it's losing one electron. This is 3. So it's losing 3 electrons, it's losing 4 electron, 5, 6, 7. Now they're all losing electron. But funny enough, they are all the same compound really, but they have different color each time they lose an electron. Why? It's because again the slot of electron is different. So because of this, the color changes. See, and in fact, some of this color might not even be there. I mean, it's not that it's not there. It's just it's invisible under how to say certain wavelengths. Yeah. For example, some chemical, like let's say some alcohol group, they they might not change color. For example, because they are already, for example, they're translucent, and then you do some measurement or you heat up the how to say the molecule, the compound, and you know right away that the compound will be different in color, or or not to say different in color, just to say different in molecular structures. But because the color is invisible, and I mean translucent, and then you have another one which is like a new molecule after you heat up the molecule. I mean the first molecule, the first alcohol. So now um, you look at the, how to say, the molecule again, that it looks invisible. This is actually due not because it changes color. I mean it changes color, yes, but it's in a color that we cannot see. It's actually changing maybe in IR range. Whereas it's actually common thing to happen in a what do you call this, in organic molecule. So yeah, it's a common thing. That's why you want to use IR spectroscopy most of the time for organic molecule. Let me check something. Yeah. Okay. Okay. Let's continue. In fact, this actually this reaction is actually quite important because not to say like all this reaction also gave out some output. It also actually helped some some organism to live. For example, this is a concept of photosynthesis is a bit hard to understand, I guess. But just to say like for this is actually simplified version of reaction of light with some molecule. In fact, sometimes it changes the structure of the molecule itself. For example, this we have dichloro. Because of light, it divided into two, and there's some reaction with the how do you call this, alkane, and this alkane give out this sort of organic molecule, and this actually how the reaction of light works with some molecule. And actually, in fact, this in a larger scale, it works like this in photosynthesis. Some light reacts with some molecule on trees, for example, on plants, and then this plant actually, not to say it's captured the light, it's actually, well, technically it is capturing the light, but it's just transmuting the molecule on the leaf itself to actually change the molecular structure and actually give out energy. This is what happened in plants. Why this is important is because uh, this is what you want to see when you do spectroscopy, or in fact, if you want to do hyperspectral imaging, when you look at certain wavelengths that you already know, that you want to know. So you are looking, let's say you are working on a leaf, which you know at 1,200 nanometers in IR range, that it actually there is some sort of reaction. So now you want to take a picture. So you take a picture using hyperspectral, which have this range, and you would obviously see some sort of distribution or some sort of disturbance in this wavelengths range due to this photosynthesis taking place. So this is one of the things that you want to look at. In fact, this thing of absorbing and reflecting light, or not to say, yeah, it's actually, it's a common concept. It's what we call black body process. And during this reactivity, yeah, here you can actually see some light was absorbed and reflected. This changes the structure of the molecule, therefore give out the spectral signature that we are looking at. And usually, yeah, there's a reflection and absorption. The reflection is what we call black body radiation, and exhaustion is what we call black body process. Oh, actually, it's just called black body. Basically, something is being absorbed. And typically, if you see something is black, it just means that it's absorbing all the energy. Yeah, this is this is where the term is actually, and how you reflect is actually you have like a, let's say, a bunch of like a rainbow color like shooting into an apple, and you only see red color because the only color reflected is like a few colors, which is red, orange, and yellow. This is how you see apple. Same story will goes with the lemon here. Mm, okay. Um, now, talk about spectral emission. Uh, some molecule, yeah, tend to be invisible. Yeah, some tend to be invisible, while what we can only see in different spectral range, as I mentioned earlier. In fact, let's say we are on the ground. So I have an example of image here. To be honest, I'm not too sure how it looks like in original picture, but let's assume that this is green, this area. Let me try again to use, yeah. Let's assume this whole area green, and you are looking at it at a ground level. So you'd say like, oh yeah, this is all healthy because they are all greens. In uh, yeah, assuming there's a plant here, all of it, and then you fly a drone with which have a hyperspectral camera attached to it. Then you realize that this spectral distribution here and spectral distribution here are not the same. Then you realize something is wrong here. So this is what it does actually. In fact, some molecule doesn't even change structure because oh, depending on the wavelength needed to excite it. For example, let's say your molecule is excited at only 100 nanometer, yeah, and now the light that you how to say shoot into this molecule is only ranging around 700 nanometers. So the there's a problem as well. The molecule won't be excited, and therefore it won't change. It's actually sort of an important factors because this is why illuminant is something that we want to look at. So for example, let's see your sample here, and you have a light here shooting. So the sample is excite only at 1000. I don't know why there is a line here. It's I don't know what happens. So you have like say like this, and your light only shoots 700 nanometers. Then at this point, because excitation energy started at 1000 nanometers and this is only 700, you won't actually see any effects here. So this is actually a typical reason why you want to also use halogen lamp because of how distribution is. Or maybe I can turn back okay, to the light source. Yeah, so let's say your molecule is yeah, it's just not a good example, I think. I'll just go back here. Yeah. So you see, for example, this is halogen lamp, and yeah, after 1200, the sample is not going very well. I mean, the distribution is not going well. But if your sample is here, it's very hard for you to see what's the uh, what's the molecular structure or any spectral signature here because it's the distribution. It's not covering it. So this is also one important factor that I was talking about earlier. Let me go back to the slide again. Here, this one. Yeah. So in fact, yeah, this is what I mean. Some molecular structure doesn't change structure on the light. Yeah, can't be seen as well due to wavelength needed to excite it. hmm Yeah, this is we're talking about reactivity of a molecule. And lastly, I think combining both together so we get back spectroscopy, as I mentioned earlier. There is a sample here. The way it works, there is a sample, and then there is a light shooting, and this light excite the molecule, and this molecule which return back the photon. And the photon now captured by the spectrometers and give out the readings. This is how spectroscopy work. In fact, in industry, you will see typically three type of common spectroscopy being used. First will be IR, So you can see this. This is wave number. Uh, Wave number actually is just 1/2 pi. If I'm not mistaken, it was wavelengths. I think so. I'm not too sure. Well, maybe not the good idea to write down here, since I'm also not too sure. Yep. Well, wave number is basically a signature of the IR range. Yeah. In fact, there's also another one, a spectroscopy called HNMR. This is the HNMR is nuclear magnetic resonance. But compared to IR or shooting lights, HNMR spectroscopy actually looking at number of hydrogen in the molecule itself. So, for example, here you have this is 3 plus 3, 6 plus 1, 7, 9, 10. So 2 here, 14, 15, 16, 16. So here you have 16 hydrogen. So you have to count here 1, 2, 3, 4. Not too sure. I have to look at the diagram. Usually there is a method to look at this, but this all 14 hydrogen will print it out here and give out some sort of structure. In fact, this huge, tall, how to say, peak is due to the structure. For example, this isopropyl structure also give out this sort of high peak. So this is how HNMR is. Yeah, so it's very useful when you want to look at mostly organic compound, but it's not very useful you want to look at metal. Well, metal you want to go with Raman spectroscopy, or actually IR spectroscopy works well in metal as well. In fact, I will show you how IR actually works, because this is closely related to how hyperspectral works. So, for example, here we have a wavelength here in micrometer. I. So it's basically what it is in nanometers, 3000 nanometers. Yeah, yeah, micro, yes. So you can see here at 3.5, there is a dip. This dip is actually what gave out the spectral distribution. Well, this is actually how the spectral distribution is. That because of this dip, or yeah, so this dip actually, we know that this is what sort of bending it is, what sort of structure it is, and this can tell you what kind of a molecule this is. So this is CH3, CH2, CH3, that's 4 CH2. I I think it's some sort of, it's a hexane, so yeah, something like this. Or CH3. Yeah, it doesn't matter. I'm just saying it's a hexane. This is what hexane is. From it came out from this. So now you know that there's a, due to this sort of molecular structure, it gave out this spectral distribution. Or I think this is a reflectance because it's 100%. No, sorry, this transmission. Yeah. So yeah, it's basically reflectance. No, sorry, this is absorbance because you transmit 100% and some area is being absorbed. Yeah. So this area which is being absorbed give out the molecular structure. In fact, this thing have a very, how to say, this is actually a very good method of checking what molecule it is. The thing about IR spectroscopy is that it's very good at determining what sort of molecule it is. For example, you have a lot of functional group, like alcohol or carboxylic acid, aldehyde, all this thing, they actually have a very sort of significant number of how to say significant physical structure of wavelengths that it actually give out a certain patterns in your wavelengths or absorbance, so it can helps you or can tell you the exact type of molecule. I mean, it wouldn't tell you how the structure of molecule is, but it will tell you what group it is, and from the group you can actually already deduce what sort of molecule it should be. I mean, this is why it's actually good to have IR spectroscopy, or in fact, and perhaps if you have hyperspectral in this case, when you look at this dip, you can actually see all those sort of what was the molecular structure or functional group there is on what the thing that you're looking at. And this is actually, yeah, as I mentioned, usually they all have some sort of specific wavelength number. See, for example, here you can see all this CH3, all this. Okay, this is a bit yeah, this is also a bit how to say, important to explain. So you see now, in fact, there's a functional group here, and this is, for example, appear many times in different wavelengths. This is one of factors of spectroscopy that, or hyperspectral, that I think user need to think about. This is because to say they only have one specific structure is a bit hard, because they also react with other things. For example, let me put here H2O. Yep. Now you see H2O in 700 nanometer, and then you would see again in 900. Roughly, I think 1.4, 1004 nanometers. 2000 nanometers you see as well, 2000 plus 2200 nanometers as well. Why did you see it everywhere? Uh, this is because the molecule tuck as well. It sort of move like this. So because of this movement, so for example, okay, let's just draw another one. Let me try again. Let me try again with this as well. Okay. I'm just gonna redraw water. So that's the best sample. At some point, it doesn't matter. At some point, this become very long. This become very short. At some point, this one become very long. This one become very short. Because it's tugging. It changes something what we call the well, it's actually changing the molecular structure or electron distribution, and because of this, it would actually tell you at different number of wavelengths. So in fact, this is actually common. So how do we control this? So it give out only certain wavelengths. So you can actually know this by controlling the how to say, surrounding factor, meaning your temperatures, your lighting conditions, etc. Because it's always stuck, and actually temperatures play a huge role, because the more heat you give out, the more sort of vibration happens, and it will give out all this more intrinsic detail of wavelength. So this is not the best idea to do this. In fact, usually you would want to enclose your area of surrounding, to actually lessen out the noise, basically the effects of surroundings in your readings. So yeah, basically that's how spectroscopy works. So now we are going to the concept of hyperspectral. So these important parts of the seminar. Okay, So we're first gonna start with imaging system. Imaging system is basically details or how actually camera works. So camera is very simple. So you have a I mean normal camera that we use on daily life, uh, on our phones or our DSLR or a normal camera basically. Typically they all have these three filters, which is blue, green, and red. And what happens is that light, when you have a light shooting, it's shooting at a lot of wavelengths, but actually what we do is that we capture only blue, green, and red. So typical example of how this works will be like this. Let's say I have here. Um, can I change the color? Oh, yeah, okay, let's see. Yeah, I think it works. Blue. Mm, yep. Oh my god. Ignore that. Okay. A blue filter. And then I'll try to change another one into a green filter. Okay. Mm-mm. Mm-mm. Yeah, green filter. And then you would have another one, which is a red filter. Okay, so I'm gonna put a color that may be brown. What happens is that your when you take a picture, you have a sensor here, and when you take a picture, it travels past through this one, and this one actually carry a myriad of photon. A package is actually what we call it. Basically, a jumble up of different species, or well, not species, I guess, different wavelengths of photons, I guess, mix up to become one package. So it's basically a wave package entered first filter. Now, blue filter is, if I'm not mistaken, it's around 400 nanometers, let's say. Uh, so it will actually catch only blue wave. So let's say this all entering, this is everything. This is basically from 300 to 700. Yes, it's the visible range. Now this, what happens is that it will only capture, I think, around 400 something, 400, and then bam, it pass through it. And then this will capture, I think, around 600, let's say, and then pass through. Everything will pass through again. Now here it will capture around 700, I guess, something around this range. Um, so all this captured, how to say, the rest will pass, and all these three different filter will eventually build an image. Will give out the build up of an image on what is actually captured. In fact, I will show later. In fact, I just want to explain how normal camera works. So now I think we'll go to another one. Slides, yeah. So in fact, when you talk about camera, there is also a lot of sort of camera. There is so typically when you talk about camera, you are actually talking about a device which can capture photons, and technically, lux meter is considered as a camera because it's also capture all the light. But instead of capturing all the light, I mean, sorry, no, capturing the colors, actually capture all the light and calculate the intensity of light. There's also luminance camera, sort of works the same like lux meter, but it actually looking at photons lux, which correspond to human visual. So it's a bit different from a normal camera, but also a bit different from lux meter. And of course, you have an RGB camera, which is, as I mentioned earlier, is basically filtering out red, green, and blue photons, and eventually build up an image of red, green, and blue photons. And also you would have a spectral camera. This is actually a hyperspectral camera, which actually capture all the photons, but within a certain range of wavelengths. So let's say your camera is from 300 to 1000, so you only capture 300 to 1000, and the rest would just fly away. And the last one, you will have infrared camera. Infrared camera usually is the same story as the spectral camera, but you are actually looking in infrared range, typically used in mining or actually in thermal camera, because our body, actually humans, not to say human, I guess. Well, yeah, human. We actually glows because we ourselves, we vibrates, but we vibrates at this very molecular level that the reaction of some of the how to say molecule around us actually give out the heat signature. So yeah, that's infrared camera. That's why it's actually good for as a thermal camera, because the hotter you are, the more you vibrates. Actually, so yeah. Okay, so but we want to talk about hyperspectral camera, yes. So yeah, we have to go back to this whole idea of hyperspectral or spectroscopy. So you need to understand that a hyperspectral is actually just a spectroscopy, but in a camera form. So as I mentioned earlier, we have the RGB camera. Typically, will catch this red, green, and blue channel, while basically capturing all this photon and eventually build up an image. But hyperspectral, as you might know, is actually not. I would say it's the same concept, but instead of just three different filter, it is actually capturing a lot of different filter. Not just to say, well, this is very specific wavelengths, right? But for hyperspectral, each layer correspond to certain wavelengths. So for example, here you have a red. This is might be, let's say 610. Yes, and then maybe this is 620. So you know that it's like 10 nanometers. How to say? Difference or range of the average of the spectral. So this is how hyperspectral works. You're actually capturing all those filter in a lot of wavelengths in different colors. It's not to say RGB anymore, it's every colors basically. And the way that hyperspectral camera works is basically you would have each pixel actually to be captured. Each pixel here actually contain a specific spectrum, specific information, and this information, it's basically capturing every pixel line by line to eventually create the whole image. And by having each pixel, you can tell what is there based on what spectrum and what location because of the pixel. So you can actually learn the coordinates of the pixel itself. So yeah, this is the best way to actually identify molecule using camera. Actually, most of the time, I think this can be used more on how to say material. If you want to identify what kind of material you're looking at, etc. So yeah, this would be the best way. Um yes. So in fact, this image is actually very huge. Some of the image can goes up to a few gigabytes. So in fact, I did some testing before, and I think I took like 5 image, and it's already like 7 gigabyte of image. This is because of how massive the data is. Because you are not taking picture only in certain wavelengths, you're actually taking picture in a very huge filter. Well, not filter, I guess. Yeah, actually, like filter. You have a lot of filter in different wavelengths. So, in fact, hyperspectral also will provide this thing what we call a data cube. So all this sort of filter catch one image of that certain wavelengths, and you actually build out the whole image, and then you would have the whole entire book. So I call it the data cube is. So each of this, you can see here there is a book. This each book is actually a specific wavelength. So each wavelength will be one page. So if you have 200 page, meaning you have, I would say, well, 200 wavelengths data. So yeah, that's how big it is actually. So yeah, this is what kind of data does hyperspectral actually provides, or what actually are we looking at? Mm. And in fact, there's a lot of type of hyperspectral camera. The first will be the push broom. So push broom is actually a common one that we're actually looking at right now. I mean, when we talk about specums. But there's also whisk broom. Whisk broom is actually used by satellite a lot. Uh, unlike unlike push broom, which you scan line by line, whisk broom actually looking at a few points, a few collection points randomly. This is actually a typical example when you want to use satellite and when you're taking picture and you learn that the Earth is curved, so you wouldn't want to focus it at one point all the time because your sample is moving as well. I mean your Earth is rotating, so that's why you want to use Whisprom, basically checking a few points randomly, not at the same time though. It's continuously. Eventually you build up an image. And then you have a snapshot. Snapshot is basically you have a image frame. You're actually taking picture like a normal RGB camera for snapshots, but for snapshots it's a bit more complicated. This actually take longer time because you actually also need to take a lot of pixel at the same time, and you have to take it a few many like a lot of time. Basically, let's say, okay, how does it work? Basically, let's say you have 300 to 1000 nanometers camera. So first of all, you will take 300 first, and then you change your filter. You will take 320, and then change filter again, 340. Change filter again, 360. This is how it works. So it's actually not very efficient, and actually it's very hard to find a hyperspectral camera that uses snapshots. And then another one, we have a staring or tunable filter. This is actually what we're looking at when we want to use a specific wavelengths. So typically this is actually common in a multispectral camera. You have a very specific wavelengths you want to look at, and you're not looking at everything at once. So yeah, this is the staring type of hyperspectral camera. And then you have Fourier transform. So Fourier transform wouldn't be really a thing we call a how to say no, normal spectroscopy uses Fourier transform because you generally don't really care about other spectrum. For example, you are looking at 300 or let's say 400 nanometers. You know already that your molecule works around 400 nanometers, but because of this 400 nanometers that you want specifically, you said to yourself, like, I don't care the rest, like 600 or below 400, let's say 300. So you just want 400, and what you do is that you want to look at this thing whether or not there is a frequency at 400 nanometers. So you use this function called Fourier transform. Typically, this would help to give out a specific frequencies. So I can perhaps maybe there's an example for this. The let's see. Yes, this is typically what it is. For example, so you have all this noise. Eventually, it will just give out specific wavelength. This is where you want to look at. You can open it. Yeah, typically this is how Fourier transform works. So you want to convert all this to become this. So as I mentioned, that's why it's not really an image that you're looking at. You're actually looking at a frequency. This is how FTIR works. It helps in spectroscopy a lot. And lastly, tomography. This is a bit more of a stitch patch and stitch. It's like one of those Google Earth sort of method where you catch one area and then you catch again another area and then you combine it together. Yeah, this is a few type of spectral camera. I would say the most important or the most common one would be the wrist broom and push broom. Yes. So how does this work? I mean push broom. So since we're talking about specums, there's actually what we call collimators. So collimators is this part. So first of all, you would have a light entrance. So generally, light would enter your collimators. Uh, Here, let me show you. Here, yeah, somewhere here. And then you would have something called diffraction grating. Well, yeah, it's actually not grating. I guess it's more of a diffraction tools because there's a lot of diffraction tools. Basically, trying to split your light into a lot of components. So typically you want to split, let's say you have 300 to 700 nanometers, but you want to look at wavelengths at 310. So you need a diffraction grating which can split the light at 310. This is actually how your uh, spectral distribution is being split. I mean, how your light being split into its significant features is from this diffraction grating. Typically it's somewhere here. And then you would have collimators. Collimators means like actually when you split the light, it actually flew up in a long direction. You typically don't want this to happen because you don't want to lose some of the light. So you have this thing called collimators to actually combine them back. It's not really combining back, but it gave out create like some sort of tunnel so that the light will flow in the same direction back here to this yeah, inspected optic. It's actually inspected optic is the parallel collimators, and it gave out and it eventually hit the sensors. So moment. And then you have lens, of course. Lens is typically you have a lens which you just want to build up an image and collect photons, or you can have like depending on how you want to collect lens as well. There's this one important factor that you want to think about when you are collecting lights is how sharp is your image as well. Unlike normal camera, which you can tune the how to say uh, the focus of it, spectral camera is a bit hard to say because you generally don't really see the image. You will just you have to try it to see how sharp it is. So lens is one thing that you need to know. I mean, you need to think about. I mean, it's hard for me to say if we are not going through the actual example of it. Mm, but yeah, as long as you can focus on the image, it should be fine. And lastly, should be the sensors. The sensor actually come in two different type. One is CMOS, another one is CCD. This typically is just normal sensors, just different method of collecting lights. Yeah. Okay. So now push broom method. Uh, so as I mentioned earlier, that we actually catch 1 pixel by 1 pixel. So push broom method, you actually capture one whole line, eventually a lot of line to build up the entire image. So this is actually how normal push broom method works. So I get it. This is actually quite straightforward. Thing. Let me see. And then yeah, hyperspectral camera eventually tell you each pixel will give you a specific wavelengths, and you can run analysis on this. Yeah, there's that. There's a method of measurement though. There's three different type. So one, if you like, is actually emitting photons that you can catch directly. But there is one which you capture something which doesn't emit photons, so you have two illuminance. So I'm saying a constant illuminant is the best practice when you want to capture a spectral distribution or spectral reflectance. Another one will be a translucent image, which you have a illuminant at the back. pass through the surface, and eventually you catch the image. Yes. So typically, when you do spectroscopy, of course, as I mentioned earlier, you should already know what kind of molecule you want to look at. As I mentioned, if your molecule react, let's say in 2000 nanometer IR range, and your camera only goes to 1000 nanometers, you're not going to catch the image of this molecule that you're trying to find, because it doesn't work like this, because it doesn't react at this range. And this is why there's actually a lot of different type of camera. I mean, it's not different type of camera, they're all the same camera, but they all have different wavelengths. They all have different specification of wavelength range, meaning they can cover different type of molecule and different type of structures that you might want to look at. So yeah, it's a lot of type camera here, you can see. Yeah, and again, this is how you want to look at. For this is just an example. So I actually take this sample from Spectrum himself. They have a few different type of green stuff. Basically, they want to see it in apple, but there's actually some apple, some green paper, and real apple, and some black material. But you can see, even though they all are greens, I mean, you can't tell the difference really. But you can see from the spectral distribution, it's actually a difference. It's just an example of how hyperspectral camera works. Yeah. Yeah. So, and lastly, when we talk about spectral camera, you also want to talk about difference of hyperspectral versus multispectral. So in fact, they both actually, or generally, the principle of working is the same. I mean, you take a picture, you have an image of basically you have the data of the picture, but it's in different. They are both in the same form, which is the spectral distribution, but they provide different data, because one, for example, hyperspectral give out the continuous spectrum, because it's actually capturing a lot of wavelengths, a lot of wavelength point, but multispectral usually just give out like very few actually. Typically 5 spectrum, so you ought to choose which spectrum you want. This is actually how the tunable filter work, but tunable filter still, I mean, you can actually change the spectrum you're looking at compared to multispectral. Usually there is specific type of spectrum you are looking at. Yeah, and this actually helps because it will tell you a lot of missing information. For example, you can see here the hyperspectral have a very common, or how to say, a more continuous spectrum. And you can see here the bumps, such a important detail, as you can't really see it in multispectral because of some, well, information loss. So this is actually a disadvantage for a multispectral, because there's a missing information here. So therefore the information provided is not accurate compared to hyperspectral camera. But yeah, so quite I think it's quite straightforward to understand what's the data characteristic of two different things. I mean, hyperspectral and multispectral. But you know, this is two different things. Not to say that hyperspectral is the way to go, because hyperspectral could get very expensive compared to multispectral. And well, this is because of a few different things. I would say if you already know what you're doing, for example, you are venturing out and you already know that, oh, your specific wavelengths react at this, oh sorry, your specific molecule or your specific compound react at certain type of wavelengths, it's generally a good idea to go cheaper version, which is a multispectral. But if you don't really know and you are walking in the uncharted territory, so it's better to go hyperspectral, since you are not sure what you're looking at, and it will help because usually hyperspectral have a very narrow bands of resolutions, so you can see more stuff in your image. And there's also, how to say, more information basically, because, well, again, you're actually looking at continuous spectrum. But there's one downside though. Typically hyperspectral have a very low volume of case study. Generally this thing is quite new, and the case study is very less, given that not many people are actually using it. So typical example will be very hard to get. For example, if you're working with, say, pineapple, then how many people in the world are actually studying pineapple using hyperspectral? So this is a bit of an issue that hyperspectral come up with. I mean, not come up with, it's just came with. And there's multispectral actually have a lot of case study. I mean, a lot of people are already using it because it's been in the market for a longer time. But the problem with multispectral is that the flexibility, because as I mentioned, you should already know what you're looking at if you want to work in multispectral, because there's only specific how to say, wavelength range that you're looking at. You're not looking at everything. Yeah, but generally it's low cost, so that's why if you already know what you're looking at, it's just a better way to go. It's actually multispectral. Um, yeah, so I think that's the difference between two of these. And now the last one will be the data acquisition and analysis. So typically this would be how we will discuss a bit how data analysis would work in how to say, in hyperspectral, because it's not actually straightforward, to be honest, because a lot of things need to think about. Like, for example, what if your image have noises, different parameters, for example. So first of all, let's look at the analysis technique. In fact, for specums, there's 4 type of analysis technique. So first of all, we PLS, partial least square. Then we have PCA, the principal component analysis, and you have RGB. This is CIE based. You are actually following the CIE, and the last will be the custom calculation. So when you work on this, you usually, I mean, in specum, usually, actually in software specum inside, there's only PLS as a method of analysis for algorithm training, because this is the fastest way basically, and so far it's the best way. I wouldn't say the best way because there's other methods as well, but one of the generally simplest and yet better way to analysis. There's a PCA as well, but PCA is not really to do modeling on. It's basically more of a study. You know, you're trying to understand your components, or your, how to say, well, you're trying to understand what you're looking at first, and then you have the RGB. Of course, RGB is straightforward, really. You're just looking at the color, but not a good way to look at IR range, because RGB in the end of the day is something that you can see. And lastly is custom calculation. It's actually more of an indexes that you already have. For example, you want to look at vegetation index, so you use custom calculation. Yeah. Okay. So maybe I can get more into this. So partial least square, the PLS, is actually it's what we call discriminant. It's actually discriminant analysis. So what happened is that it identify a specific type of sample and consider everything wrong. Let's say a good example would be, let's say you have a room, yeah. So you have x, y, maybe x, y, z, z here. It's going x here, y, x, and then maybe actually more q, q. Okay, so generally you have X, Y, Z, and Q in one room. Yeah, all in one room. Yeah. So you said to yourself, I just want X. And so what happened is that using this understanding, you just want X, PLS will consider Y, Z, and Q as the same thing and X as a different thing. That's why it's called discriminant analysis. It means that X will be A, Y, Z, Q will be B. It's a good idea to do this because you generally don't waste time to sort out everything. You just want one thing, you do only one thing. So this is how usually the PLS method works. Yeah, as you can see here, select a prominent component A and classify everything else as B. Yeah, because it's a discriminant. You choose one and the rest is no. Uh, it's actually a very best way to discriminate main object because you sometimes you don't really, as I mentioned earlier, when you want to do the Fourier transform, you generally don't care about different uh, wavelengths. That's not too important. You have your specific that you want to look at, so you just focus on that one, and the rest you consider as noise or something that you want to discriminate against. But the problem is that it's quite long because you really have to train it and find the best example. Yeah. So this is what PLS is, and then maybe I can go on with PCA. PCA is generally something almost not similar really. Uh, okay. So PCA, the way PCA works is that maybe actually it's a good example again to use. X, Y, X. Y, Z, Z, Z. Okay, so you have a bunch of lines. Another one, Q, Q. So PCA, yeah. So you have X, Y, Z, Q. The way how PCA works is that it looks at the signature or similarities. This is actually a good example. So you have X and Y. You see, X is just like this, and Y is like this and this. They looks almost the same. So PCA would say like this is almost same distincting component. So for example, this is a Venn diagram. Now this will be attached a bit, so it will consider this is as almost the same. Good for customization because it will tell that this is totally different, things is totally different. But PCA takes some time to calculate, and in fact, yeah, some of it's actually you actually really have to work on it because yeah, so sometimes you already have point of interest, meaning what you want to look at, but because of this crossover, almost same similar structure, it will identify it as something else. So it's a bit of a problem, but actually it helps with more classification. But in fact, this is generally not being used in modeling because it takes some time to do this. Furthermore, it actually, how to say, it actually not a good idea since when you do processing, you want it to be faster, and it's also not a good point when it identifies something else as something else. For example, X and Y, they might be identified as the same thing. This is one problem with PCA. But generally, if you're not sure what you're looking at, let's say this is a new sample you're looking at, and you want to know right away the difference, you can use PCA. And moving on, you have RGB based. So this is very common. You want to look at LLB values. It's commonly used in spectrometers already. I think this is very straightforward. The custom calculation is you want to look at indices. So, for example, you have NDVI. So you have this. I think it's not mistaken. It's red plus green. Oh, there's a calculation for this. So depends on what kind of spectrum you want to look at. I mean, there's some indexes. You might find it online though. But this is one way for analysis. Another way would be you can use MATLAB or a Python programming. So MATLAB is generally a very good way to do image processing because MATLAB have this what we call sampling positioning. It can combine the concept of FTIR into your analysis. Generally, FTIR is actually a very good way to identify molecule because it's simplified. You don't want to look at the certain wavelength, so you want to look at a very specific wavelength, so you use FTIR. It's same story for MATLAB. You can even find a trend for. Yeah, and it's also better integration if you have a different type of format of data. Another one will be Python programming. It's also a very good way to actually do analysis because you can break down each pixel into very specific spectral signature. Let's say you know that your wavelengths you want to check is around 300 to 400. You don't want the rest, so you want to make the processing faster, so you can just cut it off and just analysis in 300 to 400 right away. And it's more flexible for integration with other software or hardware compilation. I mean integration. Yeah, but all this is actually not supported in Insight. This is actually more of a general overview if you want to further your research more. Okay, so in Spectrum Insight, in fact, you're actually using PLS, as I mentioned earlier, for modeling. This is the reason why PLS is generally a what we call a supervised technique, meaning that you are the one that actually set the parameter compared to PCA. And as I mentioned earlier, PCA generally makes a lot because some signature looks very much the same. It's just a difference, maybe too little. So, so, but PLS usually supervise that you can actually check what's happening, and it actually help that it reduce the dimensionality, meaning that so in PCA that you cannot really control the dimension, meaning when it do the analysis, it generally classify the dimension itself, meaning that it will tell you already what's the perimeter there is in the image. Compared to PLS, you are the one that going to set the perimeter, so you are actually reducing the dimensionality, so you understand more what the perimeter is, and it generally is better at identifying type of object because again you are the one who's setting up the classes, the classification. Supervised technique is something that generally is a good idea. It's like you're training a model of your nowadays the machine learning. You have a this is actually a sample of supervised training. I mean how the flowchart works. So you are the you as a supervisor, you are the one that looking at it. So you have a training data set and what output you want, and then you train the whole thing in an algorithm, creating an algorithm. So now you put an raw data with you have label. The label is your classification, and then now you put it inside the algorithm. Eventually, it'll give out the output. This is what you want to look at. This is generally how the uh, training is. So it's in a good way that you are the one who training them, so you are looking at the same thing. But there's another problem is that overtrain, or if you feed a wrong data, it can also mean it's going to be wrong for the rest of the search or the processing. So it's yeah, but that's why you want to call it supervised training, because you want to also look at the training that you're looking at. Well, so when you're doing analysis, it's actually there's a few general steps that you should do. First of all, of course, you need data scaling.
Data scaling means that when you feed the data, you don't want to feed too much random data. Or say for example, you are doing search on potato. All your data must be in potato. You can't just do it potato today and then tomorrow you decided to use something else to train it. So there will be a problem. Another thing will be also to ensure that all the features is almost the same. The rest, another thing also to know the standardization. So this will be the pre-processing and some noise reduction. So some image might have too much noise. There's a way to do this is using the Savitsky-Golay noise reduction. This all actually already features in the inside software. So yes, next thing will be the model training. So model training, again, the best way to do is actually you label all your data. You don't want to teach your data without labeling them, because then again, how would the algorithm know what they're looking at? And you should also train the relationship between features and label, because of course some of it might look the same. This is actually a bit of a problem. That's why you want to train your data with a lot of. When you want to train, you should use a lot of sample as well to train. Yeah, and generally try to find the best way to separate classes. Not meaning not to put, like, let's say you have a typical plan, yes, with say with a green color, leaf. So this leaf look green, and then you have another leaf which look green as well, but they are different species. That might not be a good idea to put them together. So because it will just identify them as the same thing. But this talking about colors, of course. The next thing will be validation. Of course, you always need to evaluate performance because you don't know if it's going to train properly. Always have to check this thing. Yes. So yeah, well, the labeling data is the most important thing. It actually helps to improve model accuracy. So more labeled data means more uh, information, so leading to more accuracy. And also you need to also identify features. Like for example, here you can see the fat contents. This is a few features that you want to think about. Yeah, like for example, here there's a plastic and woods as well. Uh, Also need to focus more uh, on labeling data because there will be chances of overfitting. So this is actually generally what we call false data. I will show a bit later on this. And then there will be like a real world presentation. Better real world presentation is because generally when you do in lab and what happens in real world is two different things. So sometimes when you are outside, you are scanning the trees, or let's say, bit hard to say this. Let's say you are in your lab, you have a plant, let's say a ginger in your laboratory, and then you do a research on it. So you take a picture of the ginger inside your laboratory. Then you went outside, you take a picture of your ginger as well outside of the laboratory. Now, typically they might have a bit different, but because of how the illuminants work, I mean, when you're inside your laboratory, you have a certain illuminant, but when you're outside, you have different illuminant. I mean, your sunlight will be your illuminant, so it will tell you a different story. But because of labeling data, you might help to get a better word representation. In fact, this is actually quite important factor as well. I'm gonna go back to the slide. Uh, when you do scaling, it's important when this kind of things happen, when you have laboratory and a real world applications. Yeah. So, of course, this thing have pros and cons. I mean, PLSDA, the advantage of it is that you can summarize a lot of data without affecting the correlation, and actually it helps. It's very simplifying the data analysis part. But the disadvantage is that overfeeding data, meaning you put too much sample, can also lead to false claim. Sometimes it's very hard to distinguish stuff. and sometimes your data might have some noise, but your algorithm would consider noise as part of the subject, as part of the things that you're looking at, and sometimes false identification can happen as well if your model is too complicated. Meaning, let's say you take an image of you're using your model based on an image which you took outside, which have a lot of noise, a lot of other properties. Like let's say you take a picture of plants, of trees, with a lot of trees behind them. This is actually not really a good idea to do, because now your model will be too complex, because you also have to remove the trees from behind as well. So this would create some sort of disadvantage, because it's already too complex. The algorithm might not know what they are looking at, and might consider the plans behind them is actually part of the subject. And real world is quite harsh for this as well, because let's say you're doing in a lab, and then you go out and your model is too complex. Again, it will affect your reading. Yeah. Now, so I think we have a last part, which is the pre-processings. So pre-processing is generally to clean, normalize, transformation, reduction, enhancement. So cleaning means like you want to check consistency. This is obviously on your parts. Of course, as I mentioned, you want to take the same picture of the same object at maybe perhaps at different angle. Uh, this is, I think, should be removed by you, by the user itself. And another one will be normalization, meaning this normalization should also be prevented by you. Basically, you don't want to take this will be the how to say the for example, the resolutions, the settings of your camera, the settings of your lightings, etc. So this will be the normalization. You don't want to have different lightings for same image, because it would help, actually it would destroy your consistency, and it would not be a fair comparison. Another thing, transformation. This is just make sure all your files is in the same format. And then another one, reduce dimensionality. This is actually the analysis that I was talking about earlier. Basically, you don't label too much as well. That will be one issue. You want to see what you want to look at only. And lastly will be the enhancement. Actually, in fact, most of this thing, there is a what we call a pre-processing software as well. I mean, methods. I mean, which already in software, the inside software. So there's a few. You can actually see here. There's derivative, max norm, min centering, min max norm, p norm, pseudo absorbance, and Savitsky-Golay. And last will be the standard variant. I will go through a few, because some is actually pretty much the same. So for example, is derivative. Derivative is something that you actually want to look at, for example, a very specific peak. So for example, here you can see at 2000 there's a very huge dip. One moment. Yeah. So this huge dip is actually maybe what is your specific features that you want to look at. That's why it's here. Okay, it's actually literally said here that to emphasize changes of spectral trend. This actually highlight the point on ages. It's because some spectral, as you know, some earlier we saw in IR range, there's a specific dip which give out the specific structure of a molecule. That's why derivative will be a good way to look at pre-processing. They would help you actually when you do some analysis. Another thing will be max norm. Max norm will be when you want to scale. This happens typically if you have like different range or different illuminance. To be honest, I wouldn't really recommend to use different illuminance, but sometimes it happens. Then you want to use max norm, meaning you want to have a same sort of spectral distribution or spectral range. and you need to scaling it to be together for better comparison. Yeah. Okay. And another thing will be min centering. Min centering is the whole concept of actually centering it. Meaning, let's say, how to say this? Let's say your specific wavelengths work around this, and you generally want to find the mean of your total spectrum, and then your comparison as well. I'm trying to find the best explanation for this. Well, let's say let's say you have different conditions. Yeah. So in your spectrum distribution, this is condition that you're looking at, and then you have another image, which is sort of the same, but have a different condition, like maybe your lightings or calibrations that may be a different camera. Min centering would be the best way to actually get everything at the same scale, so you can do a best comparison. So typically, if you're using a few different devices at once, yeah. So and then you can look at also Savinsky-Golay filter. So this is generally trying to smooth out your image. There's one problem with Savinsky-Golay is that if you smooth it too much, you also lose a lot of information, because generally all those sharp edges or sharp peak is actually information. It could be noise as well, but we we don't really know if it's noise or not. So best way, usually we always filter it, but filtering too much also, you can actually lose your noise as well. I mean, noise and perhaps some data as well. But yeah, so actually this is a good way to also uh, actually I wrote here some noise as well might be filtered, might be crucial to the subject that you want to study. Yeah, this. Yeah, typically, I can give you a good example on this. Usually, for example, if you have you're studying, let's say, food sample, and you know one is a bit wet, and one is generally not too wet, but this wetness, this water actually give out a good structure of food, I guess. Let's say. So because of this, you might not want to delete it because you want to know if it affects your food or not. But because of too much filtering, you might accidentally filter it out as well. So yeah, generally not a good idea to use too much. But that's why there is a function which you can change the derivative and the binning. So you can look into that as well. Okay, I think the last one here, yeah, this standard normal variates. Typically, this is to balance your data. So it's very useful actually when you have two different uh, sample, which is inside the lab condition. Another one would be in a normal condition, which is outside. So this is actually trying to find the best starting line. Basically, trying to create the same sort of condition, even though they have a different standard deviation. But because typically what happens is that it doesn't matter if you're inside or you're outside, your molecule should, if it consider it's the same. Let's say you are looking at ethanol inside a room, and then you go out of the room, it's still ethanol, but it's in different condition. So now this ethanol will still have the same spectral signature, but probably with some adjustment because of surrounding. So this might change. So this is why you want to use standard normal variates. Yeah. So this is a few of pre-processing, and I think so far this is what I think important for us to cover in this. So yeah, feel free to add more because I feel there might be something that I might missed out or some improvement needed on the way you're presenting it. Yeah, so I'll move on to Specking Insight on another video. Thanks.